This is the Chapter 2 and 8 test review. It covers sections 2.5, 2.6, 2.7, 8.1, 8.2, 8.3, 8.4, 8.5, and 11.1. Great, so 3 sections from Chapter 2, 5 sections from Chapter 8, and a single little section from Chapter 11. So let's jump in. We have 34 problems, and these problems are exactly associated with your 34 problems in your web work assignment. Problem 1, solve this inequality. It's a linear inequality. We're going to solve it for x by adding 3 from the left side to the right side. And so now I get x is less than or equal to 11. Well, this is the answer in inequality notation, but we're asked to report the answer in set builder notation. So we create a set, and we say it's the set of all x values such that x is less than or equal to 11. And then we close off that set. Okay, these are curly brackets. This is the such that symbol. All right. When you input the such that symbol, that vertical bar, type VERT into your solution box and it will create it. Or you could also use the tools menu on the right-hand side. You'll see the vertical bar symbol in the tools menu. Now, in interval notation, the solution set is, well, negative infinity until 11. And negative infinity always has a parenthesis with it, and 11 has a bracket because it includes 11, right? Less than or equal to 11. There you go. So I've just written the set builder notation and the interval notation for that solution. Let's try problem number 2. Solve this inequality. It says 77 is greater than or equal to 9x minus 4. And so to start, I'm going to try to solve for x, right? This is a linear inequality. I'm getting x alone. And so I add 4 from left to right. And I get 81 is greater than or equal to 9x. Okay, now I'm going to divide by 9 across the inequality. If you ever divide by a negative number across the inequality symbol flips direction. In this case, we're dividing by a positive value, so that won't happen. And 81 divided by 9 is 9. So I get a statement that says 9 is greater than or equal to x. Typically, when we get to this point and we've solved for the variable, a lot of people prefer to have the variable first and the numerical value second. So you can rewrite this as x is less than or equal to 9. That'll help your brain a little bit. X is less than or equal to 9. This is the solution in inequality notation, right? Just make sure if you rewrite it with the variable first that it still has the inequality symbol faced away from the variable, right? The inequality symbol is still faced towards the 9. Look, the alligator's eating the 9. Look, the alligator's still eating the 9. Okay, now let's go ahead and write the solution in set builder notation. That would be the set of all x values such that x is less than or equal to 9, and then we close that set. There we go. In interval notation, well, if x is less than or equal to 9, that would start at negative infinity, because it could be all values from negative infinity all the way until 9, and then we close it with a bracket, because it includes 9. Great. If you want to consider, writing interval notation, you could always write the solution on a number line to help you imagine this, right? So if I had x is less than or equal to 9 as my answer, I could create a number line where I put 9 on it, and then I would put a closed dot at that location because it includes 9, and the variable x could be anything less than or equal to 9, so we shade the space to the left of it. Okay, and this would show me that I'm starting at negative infinity, and then I shade the region all the way until 9. Because it's a closed dot, I include a bracket. Great, let's move on to problem 3. Solve this inequality. 5x plus 9 is greater than 44. Sure, I'll start by subtracting 9 from left to right. And rewriting this inequality, I get 5x is greater than 44 minus 9, which is 35. Now I'm going to divide by 5. In this case, I'm not dividing by a negative number across the inequality, so I don't have to worry about flipping the inequality symbol. I get x is greater than 7. Great. In set builder notation, the solution set is the set of all x values such that x is greater than 7. And I close off that set. That's set builder notation. In interval notation, the solution set is, well, all the values from 7 until positive infinity. So my interval notation begins at 7, ends at infinity, and to show you graphically, right, create a number line. And on that number line, place 7. And at 7, put an open dot. Because x is greater than 7, it doesn't include 7. And now shade the region above it. Because x, the variable, could be all values greater than 7. And that includes all the way up to infinity. Okay, so now the interval notation makes sense. So I highly recommend, I challenge you to graph this to help your brain so that you can see that we're starting at 7, okay, on the number line, and we end at infinity, and that's why this is the interval notation. Cool. Let's move on to problem number 4. Solve this inequality. 4 times 8 minus 2m minus 6m minus 7 is greater than 7 minus 2 times 2 plus 7m. Well, I would begin by distributing. Okay, so I'm going to distribute and distribute and distribute and rewrite everything with these distributions. 4 times 8 is 32. And then 4 times negative 2m, that's negative 8m. And then this negative sign applies to this first term and the second term. It distributes like negative 1. Okay, so I get a negative 6m plus 7. And that's greater than 7 minus 4 minus 14m. Because once again, I'm not just multiplying in 2, I'm multiplying in negative 2. Negative 2 times 2 is negative 4, and negative 2 times positive 7m is negative 14m. Great. Now that I've gotten everything distributed, I'm now going to move all of my terms with m to one side of the inequality symbol, and all my terms without m to the other side of the inequality symbol. So you could do this in many ways, but I'm going to add 14m from the right side to the left side. And then I'm going to take 32 and subtract it from the left side to the right side. And then I'm going to take 7 and subtract it from the left side to the right side. What have I just done? I just made it so I only have variable terms on the left side of the inequality and constant terms on the other side of the inequality. Because these cancel, and then these cancel, and then these cancel, right? Okay, so let's combine like terms like negative 8m minus 6m. Well, that's negative 14m. And negative 14m plus 14m is 0m. I got 0m as my answer on the left-hand side of the inequality. And then the constants are 7 minus 7. Okay, so those cancel too, right? The 7 minus 7 cancels. And negative 4 minus 32 is negative 36. Great. And 0 times m is just 0, right? So we can write this as 0 is greater than negative 36. Now, we get to this point and the variables canceled, right? No more variable was in this final statement. And if this statement is a true statement, then the solution is all real numbers. But if this statement is a false statement, then the answer is no solution. Okay, so let's figure it out. Is 0 greater than negative 36? And the answer is, well, yes, 0 is a larger number than negative 36. This is a true statement. Since it's a true statement, okay, we're going to report our answer as all real numbers. Now, the way that you do that in interval notation is you start at negative infinity and you go to positive infinity. And this is the interval notation for all real numbers. Now, once again, if we looked at this inequality statement that we found and the answer was false, like it wasn't a true statement, then we would have said that there was no real number no real numbers in the solution, right? If there is no solution, I would have entered no solution. But because there is a solution, and my solution is all real numbers, I'm entering negative infinity to infinity like this. Or I can say all real numbers, like quotation marks. Okay, so pay attention as you enter your answer that you are doing it in the correct way. Let's move on to problem number 5. Solve the following inequality. Write the answer in interval notation. So I see 63 plus 2x is greater than or equal to 5 times x plus 9. And I immediately want to distribute. Okay, and I'm going to rewrite this as 63 plus 2x is greater than or equal to 5x plus 45. This is a linear inequality that I want to move things around with. So I'm going to, I could subtract 5x from right to left and subtract 63 from left to right, or you could do it vice versa. There are multiple pathways to take right now. So I'll do it by avoiding negativity. I'm going to subtract 2x from left to right, and then subtract 45 from right to left. And why am I saying I'm doing this with avoiding negativity? I'm about to show you. Because 5x minus 2x is 3x, and 63 minus 45 is 18. And now these results that I just got are positive, right? I just avoided negativity in a way. Now, if I had taken 5x and subtracted it from right to left, then I would have had negative signs going on here. Okay, but whatever way you decide is just fine. I'm trying to get x alone, so I'm going to divide 3 from right to left. And because I avoided negativity, I'm dividing by a positive number, and I don't have to flip the inequality symbol. Life is good. 18 divided by 3 is 6. And that's greater than or equal to x. This is my final result, but of course, some of us can't handle it. We don't like to see the variable on the right-hand side of the inequality, so we're going to flip the stuff, okay? So I've got x and 6, right? 6 and x, I'm going to write it as x and 6, and I have to make sure my inequality symbol faces towards the 6, like this. Okay, so this is my answer. I'm going to report it like this. X is less than or equal to 6. The instructions say to write the answer in interval notation. And so I'm going to write it, my answer, as, negative infinity to 6. Okay, and I'm going to put a bracket with 6. There we go. So there's my solution, negative infinity to 6. Let me show you my reasoning. I challenge you to graph your inequality on a number line, because when you do it, you will notice if x is less than or equal to 6, you'll have a closed dot at 6, and then x is the variable values that are all the things to the left of 6 on the number line. And so now it makes sense why I wrote my interval notation the way I did, because it starts at negative infinity, right? That's the left-hand side of the number line all the way until 6. It had a closed dot, so I put a bracket. All right. Let's move forward. We're on problem number 6. And it says solve this inequality. This is a compound inequality, also called a double inequality, because I've got this thing that's less than or equal to this thing that's less than or equal to this thing. I have two inequalities in one single statement. Now, we want to get x alone, the variable. And so we're going to apply any changes we make to all three parts of this double inequality. Let me show you. You see this negative 3 right here? Well, I'm going to add it to all three pieces. Okay, so I'm going to add 3 here, here, and here. And I'm going to rewrite everything. Now, let's see. Negative 21 plus 3, that is negative 18. And that's less than or equal to negative 3x, which is less than or equal to negative 18 plus 3, which is negative 15. Great. So what have I done? I've just gotten rid of this in that middle section. Next, I'm going to divide all three parts by negative 3. My goal is to get x alone, so I'm going to divide by negative 3 here, here, and here. Now, because I divided by a negative number across the inequality, yes, across both inequalities, I have to flip both inequality symbols. So instead of the less than or equal to symbol, I get greater than or equal to symbols. And negative 18 divided by negative 3 is positive 5. And that's greater than or equal to x, which is greater than or equal to negative 15 divided by negative 3. Oh, forgive me. Negative 18 divided by negative 3 is definitely positive 6. That's greater than or equal to x, which is greater than or equal to negative 15 divided by negative 3, which is positive 5. Okay, so there we go. Now, I switched those inequality symbols and my negatives became positives, and I don't like this version. I prefer to have the lower bound, the lower number on the left, and the higher bound, the upper number on the right. And so I'm going to rewrite this as 5 is less than or equal to x, which is less than or equal to 6. And so that's the way I'm going to write it. So what I did was I put my upper bound on the right and my lower bound on the left, and I switched my inequality symbols so it looked beautiful. This is a great look. There we go. Now I'm going to write my solution in set builder notation. Okay, so the set builder notation is written as, well, a curly bracket with x such that 5 is less than or equal to x, which is less than or equal to 6, and then I close the set. All right, so my inequality notation is always a part of my set builder notation, right? The inequality that I found the answer for, that's in my set builder notation. And then in interval notation, the solution set begins at 5 and it ends at 6. And I put brackets around both because I had less than or equal to symbols, brackets. Great. If you want to think about this on a number line, that's a good thing. Here's a number line. And on that number line, I have the values 5 and 6. And I put a closed dot at 5 and a closed dot at 6. And I shade the region between. X is between 5 and 6. That's what this statement says. X is between the lower bound of 5 and the upper bound of 6. And closed dots because of less than or equal to symbols in both cases. Great. Problem 7. Solve this compound inequality and write your answer in interval notation. 2x plus 4 is greater than 6. Okay, well, let's solve that for x. Okay, so quickly, you're going to see this linear inequality. I'll subtract 4 on both sides, and I get 2x is greater than 6 minus 4, which is 2. Now I'm going to divide by 2 on both sides. I didn't divide by a negative number, so I don't have to swap the inequality symbol, and I get x is greater than 1. Okay, that's my first inequality solution. Then I have this or word, right? The word or. I'm going to rewrite it down below. And now I'm going to solve the second inequality. Okay, first I'm going to add 4 like this. And then I get negative x is greater than or equal to negative 1 plus 4, which is 3. And at this point, you might notice I need to divide by negative 1 on both sides, right? Negative 1x. So I'm going to divide by negative 1 across the inequality. And then I realize, wait, I just divided by a negative number across the inequality, so I need to flip the inequality symbol's direction. And I get x is less than or equal to negative 3. Okay, so I got x is greater than 1, or x is less than or equal to negative 3. Now, in our discussions of section 2.6, we talked about how to solve compound inequalities like this. Section 2.6. What we did was we graphed our two separate inequalities on two number lines, kind of like this. And then we considered the word or and what that means for our final solution. So let me show you. If I have x is greater than 1, I go to 1 on the number line. There's 1. And I put an open dot. And x is everything bigger than 1, so I shade this region. Okay, so that's this first inequality. X is greater than 1. I graphed it on the number line. Now I'm going to graph x is less than or equal to negative 3 on the second number line here. So I go to negative 3 on that number line. Okay, so here's where negative 3 is maybe. And I put a closed dot. And x is everything that is less than or equal to that. So I'm going to shade the region to the left, and it goes that way forever. Now, the word or, right, the word that I have between these two inequalities is or. It means that find the solutions that are solutions to both of these inequalities, well, either of the inequalities. So I'm going to drop all of the shaded stuff that I have to my final solution. All of the shaded stuff gets written below, okay? And so I get that -3 value right here and the +1 value here. And I have a closed dot at -3 and an open dot at 1. And then I shade all the area to the left of -3 and all the area to the right of +1. And so I have two regions that are solutions. And so we're going to write both the regions in interval notation because that's how they want me to report my answer, in interval notation. So I'll do that. And I'm going to start at -infinity and go until -3. And I'm going to put a bracket. And that's the interval for this piece. Now I'm going to write the interval for this piece by starting at 1 with a parenthesis and going to infinity. Okay, so I start at 1 with a parenthesis and I go until infinity. This is the second interval in red. Okay, this stuff, I'm writing that interval. And because it's two separate pieces, I put a union symbol between the intervals. Here's the union symbol. It looks like a U. In fact, to write it in your solutions, then just write a U for the union symbol. Okay? Great. So this is my solution in interval notation right there. That's my final answer. I'll go ahead and box it. All right, let's try another compound inequality. Solve this compound inequality and write your answer in interval notation. This compound inequality, instead of having the word or, it has the word and. And so I will train you on how to solve that. But first, let's solve each inequality separately. All right, so I'm going to get x alone in this linear inequality and get x alone in this linear inequality separately. Here I go. Subtract 1. And now I have -3 times x is less than -6. And now I divide by -3. And yeah, you're right. We should swap the inequality symbol's direction because we divided by a negative number across the inequality. And so I get x is greater than, well, -6 divided by -3 is 2. Okay, so here's the solution to my first inequality. Now I see the word and, so I write it down below. And now moving on to this inequality, solving it for x, I'm going to add 2 first. And so rewriting this, I get 2x is less than 8 plus 2, which is 10. I now divide by 2, and I find out x is less than 5. Great. I challenge you to write these two inequalities graphically stacked on top of each other. Okay, so when I see x is greater than 2, I go to 2 on that number line, and I put an open dot, and I shade the region to the left. The x variable is all values greater than 2. Okay, when I see x is less than 5, I go to 5 on the second number line. And is 5 a bigger number than 2? Yes, that's why I'm writing 5 to the right-hand side, 2 on the left-hand side. The smaller number, write it on the left. The bigger number, write it on the right. That's what I did in this last one as well. The smaller number was -3. I wrote it on the left. The bigger number was +1. I wrote it on the right. This will help you compare the graphs. Great. Well, I want to graph x is less than 5, so I put an open dot at 5, and I shade the region to the left. There we go. Now, the word and means only write the solutions where the area, the shaded regions are stacked on top of each other. So this part is not shaded over here. This part is not shaded here, right? So the only sections where these things are, the shaded regions are stacked on top of each other is between 2 and 5, okay? So I'm going to put my lower value on the left, my bigger value on the right, and I had open dots in both of those cases, and I'm going to shade the region in between them. This is the only region that shares solutions stacked on top of each other. That's what you do when you have the word and. And so my solution begins at 2 and it ends at 5, like that. This is my solution. And I put parentheses because I have open dots, right? Open dots. There we go. Let's proceed forward to problem number 9. Solve this compound inequality and write your answer in interval notation. When I see negative x is less than 4, I divide immediately by negative 1. And because I divided by a negative number across the inequality, I flip the direction of the inequality symbol, and 4 divided by negative 1 is negative 4. Okay, so my first solution is x is greater than negative 4. Now I have the word or. Okay, now let's solve the second inequality for x. So I subtract 3 first. And rewriting this inequality, I get negative 3x is less than or equal to negative 6 minus 3, which is negative 9. I now divide by negative 3 across the inequality. Because I divided by a negative number across the inequality symbol flips direction, and negative 9 divided by negative 3 is positive 3. All right, so there we go. I challenge you to draw each solution on a separate number line, right? Each inequality, go ahead and put it on a separate number line so you can compare those number lines. So negative 4 is the smaller number, so I'll put it on the left. Positive 3 is the bigger number. I'll put it on the right on the number line. And if x is greater than negative 4, I put an open dot at negative 4, and I shade the region for all x values that are bigger than that to the right. And if x is greater than or equal to 3, then I put a closed dot at 3, and I shade the region to the right. Okay. And now the word or right here implies that I need to find the things that are solutions for either one of the graphs that I just drew. And so I'll write the graph that is the solution, and it's all the shaded region that we have across these two inequalities number lines. So I'm going to be starting at negative 4. Okay, I'll write it right here, negative 4. And I'm putting an open dot just like it has. And then I'm shading all of the region to the right, all the way to infinity. Okay, because this graph already has all of that stuff up on the graph above. Okay, so this is the answer when I'm using the word or. I'm going to write my solution in interval notation like I have been. Okay, so interval notation would start at negative 4 and go to infinity. Here's the solution in interval notation. Great. Let's proceed forward to problem number 10. In section 2.8, you discussed absolute value equations and inequalities and how to solve them. So let's get started. When I see the absolute value of negative 5 times r equals negative 20, I immediately stop and I say an absolute value has to be equal when it's isolated all by itself. It has to equal a positive number. If it does not equal a positive number, if it equals a negative number, then there are no real solutions. Okay, so that's my answer here. There should be big alarms going off in your head. The absolute value of anything, whether it's negative or positive, is always a positive answer or 0. It's never negative. So little reminder for you, the absolute value of something is the distance that thing is from 0, and an absolute value's result is always positive. Okay, because when we measure the distance that something is away from 0, that distance will always be positive. We can't measure a negative distance. Great. So that's my answer. No real solutions. And I'm done. Let's move forward to problem number 11. And it looks like this. Solve this equation. The absolute value of negative 8 times t equals 16. So that absolute value is isolated. It's all alone on the left-hand side of this equal sign, and it equals a positive number. Okay, that's allowed. That's good. Now, how do you solve an absolute value equation? You have to drop the absolute value symbols by setting this stuff in the absolute value equal to 16 itself and setting it equal to negative 16. All right, so I'm going to create two separate equations. I say negative 8 times t equals 16 and negative 8 times t equals negative 16. Okay, so to drop the absolute value symbols, which is our main goal to be able to solve, we have to create two separate equations. Now we're going to solve each of those two equations, and we do it the same way. We divide negative 18 from left to right. Sorry, negative 8, I mean. So here I go, I'm dividing negative 8 from left to right. And yeah, the negative 8s cancel here and here and here and here. And I get two solutions for t. T equals negative 2 and t equals positive 2. Right? So the way I have to report my answer is to separate my answers with commas like this. This is the format right here. And so I'll write t equals negative 2, comma, t equals positive 2. Done. This is how I'll report my answer. Moving forward, let's solve this following absolute value equation. And so we see an absolute value all by itself on one side of the equal sign. And the result is positive. Okay, so we can break this equation into two separate equations to drop the absolute value symbols. Yeah, so we write this as 4x minus 8 equals 9, just like the original statement without the absolute value symbols. And then we write the second equation, 4x minus 8 is equal to negative 9. These are two separate equations that I've created. I had to drop the absolute value symbols to solve this and finish off this problem. So let's proceed. And I'm going to solve both equations simultaneously. See, I need to add 8 to begin solving for x. And I'm going to do it in both equations. And so I get 4x equals 9 plus 8, which is 17. And in this case, I get 4x equals negative 9 plus 8, which is negative 1. Now, I divide both equations by 4. Both sides of each equation, dividing by 4 to solve for x. And I have my solutions. X equals 17/4, right? It's great to write your result as an improper fraction. You love to see it. And then in this case, x equals negative 1/4. Okay, x equals negative 1/4. Let's see how they want me to report my answer. If there is more than one answer, yeah, we have more than one answer, 17/4 and negative 1/4. Write them separated by commas. Okay, so here they give me an example. And so I'm just going to write 17/4, comma, and then negative 1/4. Okay, so this is how I'm going to report my solution in this case. Moving forward, problem 13. Solve the following equation. The absolute value of x minus 3 equals the absolute value of 9x plus 1. Looking back in your 2.7 notes, there was a definition of how to handle it when you have the absolute value of something equals the absolute value of something. Let me show you how it works. You can drop the absolute value symbols when you write your very first equation. So we have 1x minus 3 is equal to 9x plus 1. Okay, so the first equation that we write, just drop the absolute value symbols. Make them disappear. Boom, 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 gone. Rewrite it. Now, in the second case, take the first stuff, right, the 1x minus 3, set it equal to the negative version of the stuff here in the absolute value, 9x plus 1. So we're gonna take 9x plus 1 and put a negative in front of it. Okay? There you go. Now, do you agree that 1x is just x? 1 times x is x? Yes. So to make your life easier, the 1x that we had, just make the 1 disappear. And now let's proceed to solve each equation separately for x. So if I were you, I would, take this equation, subtract x from left to right, and subtract 1 from right to left. That way we're getting all of our our variable values on one side of the equal sign and all of our constants to the other side. That's our strategies for solving linear equations. And now -3 minus 1, that's -4, and 9x minus 1x is 8x. All right. Now you probably see, hey, we have to divide by 8 from right to left to get x alone, and we find out x equals -4 over 8, which reduces to -1/2. Okay, so there's my first answer. And let's solve the second equation to get my second answer. Okay, so this negative sign has to distribute. And rewriting this equation, I get x minus 3 is equal to -9x minus 1. Right? So it's important that you put that negative sign and wrapped the 9x plus 1 in parentheses, distribute the -1 times that stuff, and we get this as a result. Now let's go ahead and move all of our variable terms to one side. So perhaps I add 9x from right to left, and then all the constants go to the other side, so perhaps I add 3 from left to right. And I say perhaps because there's more than one way to get it done. And x plus 9x is 10x, and -1 plus 3 is 2, and now I divide by 10, and I find out my second solution for x. X equals 2/5. Great, so I found a first solution, solving the first equation, and a second solution, solving that second equation. And so I'll separate my answers with commas. I'll write -1/2, comma 2/5. Done. Let's move on to problem number 14. And at this point, we get to absolute value inequalities. And in section 2.7, you learned how to solve absolute value inequalities with less than symbols, less than or equal to symbols, greater than symbols, and greater than or equal to symbols. And I challenge you to go back and look back at that because we're about to do a variety of problems regarding this. Now, the interval described in set builder notation by the inequality, the absolute value of 3x plus 15 is less than 15, has interval notation a comma b. And so our goal is to find the interval notation solution to this and write the lower bound and then the upper bound. So how do you do it? Well, you take this value 15 right here, and you create a double inequality, making that 15 negative on the left-hand side. And that's going to be less than 3x plus 15, which is less than 15. Okay, so this is how you do it. You take this value 15. You make it the lower bound by making it negative, and then you can drop the absolute value symbols. Okay, no more absolute value symbols between this 3x plus 15, and that's less than 15. So now you've got a double inequality set up here. And this is how you handle it when you have less than or equal to symbols. Now I'm going to solve the double inequality that I created. Here I go. First, I will subtract 15 from all three sections of this double inequality. And -15 minus 15 is -30, which is less than 3x, which is less than 15 minus 15, which is 0. Now, I'm going to divide by 3 on all three parts of this double inequality. And -30 divided by 3 is -10, which is less than x, which is less than 0, because 0 divided by 3 is still 0. Okay, so we started with this. We subtracted 15 from all three parts. Then we had this. We divided by 3 from all three parts. Now we have this. And guess what? This is the solution. But that's the solution in inequality notation. If we write the solution in interval notation, we start at -10 and we go until 0. And because we have less than symbols on both sides, we put parentheses here and here. And this format looks exactly how they want me to write my answer for A and B. Well, what is A? A is -10. What is B? B is 0. And I'm done. I've answered it. Let's move on to problem number 15. It says solve this inequality and write your answer in interval notation. The absolute value of x is greater than negative 3. Now, the format with which I convert this absolute value inequality is I write it as, well, x is less than negative 3, or positive 3, or x is greater than negative 3. Let me explain to you what I just did. To drop the absolute value symbols, I set x, I swap the inequality symbol to less than, and then I take the negative version of negative 3 to make positive 3. So my first inequality is x is less than 3. And then I say or. I put the word or. And now I rewrite this without the inequalities or the absolute value symbols. So I just get x is greater than negative 3 for my second inequality. There you go. I challenge you, when you have compound inequalities with the word or between, or the word and between, go ahead and draw your two inequalities on stacked number lines, like this. And so write the smaller number on the left and the bigger number on the right. If I'm graphing x is less than 3, I put 3 on the right. If I'm graphing x is greater than negative 3, I put negative 3 on the left. Now, I put open dots for both cases. And if x is less than 3, I'm shading all the stuff this way. And if x is greater than negative 3, I'm shading all the stuff this way. Great. And now I write my final solution. Okay, on a number line, I'm gonna write my final solution. The word or means that it's the solutions on either graph. So I take all the red stuff of the first graph and all the red stuff of the second graph, and I write that red shaded stuff on the bottom graph. And what I come to the conclusion of is that if I shaded all that stuff, that it would actually shade the entire number line from negative infinity to infinity. Okay? So it looks like my answer is negative infinity, comma, infinity. And there we go. Moving on to problem number 16, solve this inequality. It says the absolute value of 3x plus 3 minus 8 is less than or equal to 4. Great. So first, I want to isolate my absolute value, meaning get it by itself. To do that, I'm going to add 8 from the left side to the right side. And I get the absolute value of 3x plus 3 is less than or equal to 4 plus 8, which is 12. Now, to drop the inequality symbols, or the absolute value symbols, I should say, to drop these absolute value symbols, I need to rewrite this inequality as a double inequality. And I take the value 12 on this right side, and I make it negative, and I put it over here on the left side. And I put a less than or equal to symbol, and I now drop my absolute value symbols, writing the insides of it, and then I say that that is less than or equal to 12. I've created a double inequality. Now I'm going to solve this double inequality for x. To do it, I subtract 3 from all three of these parts. And I get negative 12 minus 3, which is negative 15, which is less than or equal to 3x, which is less than or equal to 12 minus 3, which is 9. I now divide by 3 on all three parts of this double inequality. And I write my result. Negative 15 divided by 3 is negative 5. And that's less than or equal to x, which is less than or equal to 9 divided by 3, which is 3. So this is my solution in inequality notation. But they want me to write my answer in interval notation. So in interval notation, I'll start at negative 5, and I'll put a bracket around negative 5. Why? Because negative 5 is less than or equal to x. Okay? Now I put a comma, and my interval stops at 3. And I put a bracket at 3, Why? Because x is less than or equal to 3. So here's my interval notation solution, and I'm ready to move forward to problem number 17. Problem number 17 says match the statements defined below with the letters labeling their equivalent expressions. You must get all of the answers correct to receive credit. Great. Looks like we've got 5 different scenarios. The absolute value of x minus 3 is greater than or equal to 7. The absolute value of x minus 3 is less than 7. The absolute value of x minus 3 is exactly equal to 7. The absolute value of x minus 3 is less than infinity. And the absolute value of x minus 3 is greater than 7. Wow. So I've got all 4 versions of inequalities here, 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 and here. And I've got an equal version. And one of these versions has infinity. We need to match it with one of these solutions. All right. So, by the way, this letter right here is just, it represents the word in. X is in this interval, or X is in this interval. Okay, so hopefully that helps you make sense of this fancy letter. It looks like an E. Okay, now let's go ahead and jump into this. How would I decide which one's the solution? Well, I might take something like the absolute value of x minus 3 equals 7 and solve it. Let's do the equation one. And so we would rewrite x minus 3 equals 7 and x minus 3 equals negative 7, like this. And then we'd solve each equation separately. So I would like add 3, and magically we've already solved for x. That's great. And so I get x equals 10 and x equals negative 4. Okay, which of these solutions had only two solutions of 10 and negative 4? I look through here and I'm like, wait, this one had only the solutions of negative 4 and 10. They're in curly brackets. When you have like a single solution, they go in curly brackets. So the answer for number 3 is D. Those go together. So I'll write D right there with 3. Okay, so that's how I found out that number 3 is matched with D. Let's try another one. I like doing the less than inequalities. Those are nice and easy, nice and fun. So x minus 3's absolute value is less than 7. What I do is I take 7, I make it negative, and make it less than x minus 3, which is less than 7. All right, so I've taken this absolute value inequality, and I rewrote it in its equivalent form. Now I add 3 to all 3 sides of this double inequality, like that. And so negative 7 plus 3, that's negative 4, which is less than x, which is less than 10. Okay, so this will be in interval notation. Let's rewrite that in interval notation. Negative 4, comma, 10, with parentheses around them. That's what it looks like. And I scan my possible solution, and wait, there it is. X is in the interval from negative 4 to 10. And those are parentheses, just like my interval notation would have. I've discovered that number 2 is the same as its solution's E, right? I'll write that, E. Now, the cool thing is, I don't have a less than or equal to, so if I had a less than or equal to, I would put less than or equal to here and here, and here and here, and I would put brackets instead of parentheses. See, like this. But in this case, I don't have a less than or equal to option. I have a greater than or equal to option, so that's a little different. Okay, moving forward, we still have 3 inequalities to decide what the answers are for A, B, and C, here, here, and here. Now, let's go ahead and play with this one. X minus 3's absolute value is greater than 7. So what I'm going to do is I'm going to take the absolute value stuff, x minus 3, and set it less than negative 7. And then x minus 3 and set it greater than 7. Okay, so I was able to drop the absolute value symbols in this case, these absolute value symbols. by setting the stuff in the absolute value less than the negative version of 7, and then I dropped it with the greater than 7. Just like is here, I dropped the absolute value symbols for the second one, and we write the word or in between. Cool, now we solve each one, and we do it the same way. We add 3, and again adding 3, like that. And I get x is less than negative 4, or x is greater than 10. Okay, and if I was to graph this on a number line, I'll do a single number line for both inequalities because of the word or. I have negative 4 and positive 10, and open dots for both, and I'm shading the stuff to the left of negative 4 and the stuff to the right of positive 10. And if I was to write this solution in interval notation, I would get negative infinity, comma, negative 4, and then union that with the second interval, 10 to infinity. All right, so I have just rewritten this absolute value inequality like this in blue, and then I solved each one like this, and then I graphed it, and I found out this is the interval notation. And so looking at my possible solutions, I go up to option A, and it's the x values that are in the intervals from negative infinity to negative 4. Yep, that matches. Union 10 to infinity. There it is. And so this number 5 option, its solution is A. Great. Next, you see how this is the greater than symbol for this inequality, and this one's greater than or equal to, and everything's the same? Well, guess what? I could drop down to the solution that I just had and change all the inequality symbols to less than or equal to or greater than or equal to symbols like this and this and this and this. And then these become closed dots, and that causes these parentheses here and here to become brackets. And that is the solution for number 1. Okay, so you see how this number 1 that we just changed everything is the same as number 5, except all the inequality symbols get the equal to below them. Here, 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 and here. These become closed dots. These become brackets. And that is exactly what option C's solution is. So I know that number 1 is associated with C. And by default, that means that number 4 is associated with this last one we haven't included yet, B. And there we go. We have matched the inequalities and equations that we see with their associated solutions. That was a big problem. Good job. Let's go ahead and move on, and we're going to solve this inequality by inspection, meaning in your head, and write its solution set using interval or inequality notation. You know what? I prefer you don't do this in your head. I prefer you try it by hand. So when I see the absolute value of x plus 5 is greater than 0, well, I immediately say, well, I could separate this into 2 inequalities. The positive version of this and the negative version of this. So I have x plus 5 is less than 0, or x plus 5 is greater than 0, like this. And I solve each one, and so I say, okay, subtract 5 from left to right. And then we get x is less than negative 5, or x is greater than negative 5. Okay, what would this look like on a number line? Well, on a number line, and I'll put both of the inequalities on the same number line in this case. I go to negative 5 on that number line, and I have an open dot, and x is everything that is less than negative 5. So here I get this stuff shaded. Or x is everything bigger than negative 5, but negative 5 was never included. Negative 5 was an open dot in this case and in this case. And so my solution set will be from negative infinity until negative 5 with a parenthesis, And then -5 to infinity, these are two separate intervals, right? They're separated because we can't include -5, and so we put a union symbol between them. So this is the final solution. Great. Okay, to finish, I would ask you, would you be able to solve the inequality simply in your head? I, mm, I recommend writing it out. Okay, we have the format that we learned in 2.7 for solving absolute value inequalities. Let's move forward, and we're now going to move on to the stuff from chapter 8, which is about radicals, simplifying radicals, adding, subtracting, multiplying, and dividing radicals, all that stuff. So let's go ahead and start nice and easy. Simplify. Assume that v can represent any real number. Okay, so when I see the square root of 100v squared, I think, what's the square root of 100? Well, that's 10. And what's the square root of v squared? Well, that's v. But if it can represent any real number, then I need v to be in an absolute value. Okay, so my answer is 10 times the absolute value of v, because our assumption is that v could be negative or positive. Great. Moving on, problem number 20. Simplify the numerical expression, the negative square root of 100. If you see a negative sign in front of a root, that's fine. That's always fine to have. And so we're just going to write, hey, that result is negative, and then the square root of 100 is 10. So -10 is my final answer. Done. Simplify this one. Assume that all variables represent positive real numbers, the square root of 18 times p cubed. Now we're going to use the product rule of radicals, okay? And the product rule of radicals says I can separate a single radical into two radicals. And the stuff you want to put in the first radical is going to be a perfect power of the index. In this case, the index is 2, the index of this radical. And so 18 is a multiple of a perfect square. And that perfect square is 9. 9 is a perfect square, okay? And it goes here. And then the leftovers, that's 2, because 9 times 2 is 18. 9 is the perfect square. It goes in the first radical. The leftover is 2. It goes in the second radical. Now let's think about p cubed. So I need a perfect square, and perfect squares have the value of the index or a multiple of the index. So p3 is not a power of 2, like a multiple of 2, we should say. And so I'm going to take p cubed, and I'm going to separate it into p squared and p. So p squared is a perfect square. It's a perfect power of the index. And then there's still a p, so that's part of the leftovers. Now I can clean up the first radical because they're both perfect squares under the square root. And so I say the square root of 9, that's 3. And the square root of p squared, that's p. And we're going to multiply on the leftovers, which is the square root of 2 times p, right there. So that's my result. Great. By the way, if you type in SQRT into your solution box, it should produce a square root symbol, and then you can input what's under that square root. Okay, so this information could help you in your input of your solution. Let's move on. Problem 22. Assume that a and b represent positive real numbers. Simplify the expression into the simplest radical form, a times the square root of c, where a and c are either integers or monomials. And this is a fourth root. Okay, so our brains have to think in perfect fourths to simplify this fourth root. Okay, and we're going to use the product rule of radicals again. So we're going to turn this fourth root into two separate fourth roots. And under the first fourth root, we're going to put perfect fourths. And under this next fourth root, we're going to put the leftovers. Okay. And so I look at the number 28, And I think, is there a perfect fourth that multiplies, that 28 is a multiple of? And in my brain, I have a hard time seeing if there is such a value. I don't think so. So I'm gonna put 28 in the leftovers. Because think of perfect fourths, like 1 to the fourth is 1, 2 to the fourth is 16, 3 to the fourth is 81. We're already well above 28. 28 is not a multiple of 16. I got stuck, so I put 28 in the leftovers. Next, I think about a cubes. Well, this power of 3 is less than the index value. So I'm going to put a cubed over here in the leftovers. And then b to the fourth, that is a perfect power of the index 4, right? So I can put b to the fourth in this first box right there. And so now I write my answer. I've got the fourth root of b to the fourth, which is just b. And then I have the leftovers, the fourth root of 28a cubed. Okay, so there I have it. And now I'm going to write my result. This stuff in front of the radical, that's just b. That's all I could get out. And the stuff inside the radical, that's 28a cubed. Awesome. Moving on. Problem 23 says find the distance between the 2 points. Now, these 2 points, we can call them x1, comma y1, right? x1, comma y1. And the second point is called x2, comma y2. And to find the distance between 2 points in space, we can use the distance formula, which is the distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. This is the distance formula that we learned about in section 11.1. Okay, now we're going to input the actual values. So the square root of the difference of the x's. Now, the difference of the x values, I'm going to take x2 and subtract x1, so that's 4 minus negative 3. 4 minus negative 3. And I square that, and I add it with the difference of the y's, right? y2 minus y1. y2 is 6, y1 is 7, so I take 6 minus 7, and I square it like this. Great. Now, when you have a double negative, we have the minus sign of the formula and the negative value, right, for x1. So we got a double minus. So just turn that into a plus sign. When you subtract a negative, that's addition. So cleaning this up, I now have 4 plus 3, which is 7 squared, plus 6 minus 7, which is negative 1 squared. And 7 squared, that's 49. And I add that with negative 1 squared, which is positive 1. So my answer is the square root of 50. Now, that can be simplified. So I'm going to simplify this radical. 50 is like 10 times 5, but 10 is 2 times 5. So 50 is 2 times 5 times 5. And so it simplifies to 5 root 2. Okay. Now what you could do to clean this up, you could use the product rule of radicals and separate 50 into a perfect square and the leftovers, right? Because 50 is 25 times 2, and 25 is a perfect square. And then you can write the square root of 25 is 5, and then you got the square root of 2 multiplied on. There you go. So this is the exact distance, 5 times the square root of 2, the exact distance between this point and this point in space. If you get out your ruler, that's what the answer would be. Great. Problem 24, consider the 2 points, 2 comma negative 1 and negative 5 comma negative 4. The distance between them is what? All right, well, we just used the distance formula, so let's get it back out. The distance between these 2 points in space And by the way, we can call this first point x1 comma y1 and the second point x2 comma y2. So as we put the difference of the x's under a square root, we would take -5 and subtract 2, right? And then we could square that, and then add it with y2 minus y1 squared. And yeah, we had the subtraction sign of the formula and the -1 value after, so this minus negative becomes a plus. Do that in red, boom, boom. And let's clean this up. So the distance between these 2 points is, -5 minus 2, -7 squared. Plus -4 plus 1, well, that's -3 squared. And -7 squared is 49. -3 squared is 9. And 49 plus 9 is 58 under the square root. So we got the square root of 58. Okay, great. Now, the x-coordinate of the midpoint of the line segment that joins them is blank. Well, to find the x-coordinate of the midpoint between the two endpoints, we take the x values and add them together and divide by 2. Just take the average of the x values. Right, so I'll show you generally how we do it. x1 plus x2 divided by 2. And that equals, well, 2 plus -5 divided by 2. Right? So I'm taking 2 plus -5 divided by 2 to find their average. And 2 plus -5 is -3. So I end up with -3 halves. Like this. Great. Okay, to find the y-coordinate of the midpoint of the line segment that joins these 2 points, I would take y1 plus y2 and divide it by 2. Okay, y1 is -1, y2 is -4, so I take -1 plus -4, and I divide it by 2. And -1 plus -4 is -5. Okay, so I get -5 halves for the y value of the midpoint. Okay, so what is my midpoint, for this whole thing? The midpoint between these 2 points is the x value -3 halves, comma, the y value -5 halves. Okay, so this is the coordinate in space that is the midpoint between these 2 given points. Great. Problem 25, find the point on the x-axis that is equidistant from the points 2, 3 and -5, 7. Okay. So quick detail, we need to find the location on the x-axis that is the same distance away from those 2 points. Now let's think visually in space. So I want to help you see this visually. If I have an xy coordinate system, and I go to 2, 3, 1, 2, up 3, 1, 2, 3. Well, that point is right here in space, 2, 3. And then -5, 7 would be 1, 2, 3, 4, 5, and then up 7, way up here, like that. So the question is, what point lies on the x-axis that is the same exact distance from these 2 points? And one thing that you could consider doing is just thinking like, okay, if we create like a right triangle like this, right triangle for this situation, and a right triangle for this situation, when will the hypotenuses be equal to each other? At what location on the x-axis will this hypotenuse of this right triangle be equal to the hypotenuse of this right triangle? And it seems to me like it would be somewhere around like -3 here, somewhere around -3, because I'd have a value of 7 and 2, and then 2 and 5. Yeah, so that point is somewhere close to like -3 comma 0. That's going to be kind of my guess. This is a challenge problem that I'm going to leave you to think a little bit more about. Some of your problems are a little harder than the other ones. Good luck. Problem 25. Here we go. Problem number 26. The expression 16 times b to the 1/2 times 2 times b to the 1/4 equals n times b to the r, where n is the coefficient and r is the exponent of b. Now we need to simplify this. And to do it, all we need to do is apply this half power to both of these bases, 16 and b. So that's 16 to the 1/2 times b to the 1/2, okay? And then that's multiplied with 2 times b to the 1/4. Great. One important detail to notice is this rational exponent of 1/2 is outside of the parentheses. So it applies to both the bases 16 and b. And this one's in parentheses, so it only applies to b. Okay? Now a 1/2 power is the same as a square root. A rational exponent is a radical. So the square root of 16, that's what this is. 16 to the 1/2 power, that square root is 4. And then I'm going to multiply that by 2 because multiplication is commutative. So I'm going to take that result of 4, multiply by 2, and then multiply my bases of b, like b to the 1/2 and b to the 1/4, like this. And so 4 times 2 is 8, and b to the 1/2 times b to the 1/4 is b to the 1/2 plus 1/4. We're going to use the product rule of exponents, okay? So at this point, we're going to add 1/2 plus 1/4 for the exponent, and 1/2 plus 1/4 is 3/4. Great. So in the coefficient, right, in this case, right, looking at n here, that is 8. So that's my answer, 8. And then r, that's the exponent of b, right? That's this exponent right here. Well, that's this exponent. That's the resulting exponent of b. So I'm going to answer, that answer is 3/4. That's the exponent. Great. Problem 27. Simplify this. If 25 times r squared to the 1/2 equals a times r to the m, then a equals blank and m equals blank. So since 25r squared is in parentheses and raised to the 1/2 power, the 1/2 power applies to the base of 25 and it applies to r squared. So I'm going to write the result as 25 to the 1/2 times r squared to the 1/2. What am I doing? I'm using the power rule of exponents and I'm applying it to the first base and the second base. Now I write my result. Well, a 1/2 power is the same as a square root. So 25 to the 1/2 power is the square root of 25, which is 5. And r squared to the 1/2, I use the power rule, multiplying 2 times 1/2, and that gives me 1, a first power. Now let's associate this with how they want me to write the answer. Well, this a, right, is 5. So that's my answer, 5. And then this m is 1. It's the exponent. So m equals 1. And these are my answers. Problem 28. Match the radical expressions below with the letters labeling their equivalent exponential expressions. Great. So we have learned in section 8.3, 8.3, that we can turn radicals into rational exponents. Okay, radicals and rational exponents are the same thing. And so we take the base a and we take these values of the index, that's the denominator of my fraction, and this power of a, that's the numerator of my fraction. And so I get 4/3 as my rational exponent. Okay, so looking at my solutions, wait, that's this one, b. Okay, so I'm going to answer that number 1 is associated with the, b. Okay, I'll write b above number 1. Okay, looking at number 2 here, I see the cube root of 17 squared, and I'll rewrite that as a rational exponent. Okay, so I'm going to write this as 17 to the 2/3 power. The index is the denominator of the rational exponent, so I write 2/3. Okay, now I look at my possible solutions. Do you see 17 to the 2/3? Yes, I see it. It's right here. It's option A. Okay, so this one, number 2, is option A. Let's move on to number 3. And I see the reciprocal of the square root of 17. Okay, now, if I were you, I would rewrite this as 1 over 17 to the 1/2 power. Okay, the square root of 17 is 17 to the 1/2 power. Where's the 1 and the 2, you ask? Well, they're invisible. The first power is right there, and the index is 2. It's a square root, so it has an invisible index of 2. And so that's where the 1 and the 2 are for this 1/2 power, the rational exponent. Okay, now you've also learned that the reciprocal can be written as a negative exponent, right? So if I see 1 over 17 to the 1/2 power, I can rewrite that as its reciprocal, 17 to the negative 1/2 power. Okay, so negative exponents act as reciprocals. So when I look at number 3 and I try to match it with all my possible solutions here, I notice, wait, 17 to the negative 1/2 power, that's option E. So number 3 is associated with option E. Let's look at this next one. Here's a radical. Let's write it with a rational exponent instead. Okay, so the 4th root of 17 cubed is 17 to the 3/4 power. Remember, the index is always the denominator. This power is always the numerator. And so looking at my possible options, that's when I finally look at my possible options and I say, oh, that's C. And of course, we've already used B, A, E, and C, so my last option will be D, but let's prove it. So when I see the 4th root of A cubed, I rewrite it as A to the 3/4 power because this index of 4 is the denominator of my fraction. And that's exactly what it looks like in option D. So we have matched all of these radicals with their associated solutions. Let's move on to problem number 29. Simplify the expression and use the square root SQRT with parentheses for the square root symbol. Or you could look at your tools menu on the right. It has the square root symbol as well. So when we see 8 times the square root of x plus 6 times the square root of x, our brains tell us that these are like radicals. You learned about like radicals, that they can be combined together like terms. And like radicals have the same index and the same radicand. So the index in both cases is 2. Yeah, so same index. And then the stuff under the square root is called the radicand. If they have the same radicand, then yeah, we're good to go. So same index, same radicand. They can be combined together. So 8 root x plus 6 root x is 14 root x's. It's 14 times the square root of x. Okay, so there you go. Let me make this really clear. We had the same index. We have the same radicand. We can add these pieces together. 8 plus 6 is 14, and these same radicals are root x. So I have 14 times the square root of x. Great, I hope I was helpful in explaining that. Let's move forward to problem number 30, which says simplify and assume that all expressions under the radicals represent non-negative numbers. Here I have a binomial multiplied by a binomial. And whenever you see that, just think of polynomials, how you would multiply 2 polynomials together. You would FOIL, first, outer, inner, last multiplication. And so I'm going to multiply 9 times the square root of x times 5 times the square root of x. Now, 9 times 5 is 45. And the square root of x times the square root of x is just x. Like really quick, if I have the square root of a happy college student times the square root of that same happy college student, the answer is happy college student. Okay, the square root of anything times the square root of that same thing equals that thing without the square root anymore. Like, let's take an actual number. If I have the square root of 2 times the square root of 2, that answer is 2. And if I have the square root of x times the square root of x, the answer to that multiplication is just x. And so when I see the square root of x being multiplied with the square root of x, I say the answer is x. There's my quick explanation for you. Let's move on. We've multiplied the first terms together. Let's multiply the outer terms together. So 9 times the square root of x times positive 2. And 9 times 2 is 18. And I still have that square root of x in there, right? So I just multiplied the outer terms together. I got positive 18 root x. Now the inner terms of FOILing, 7 times 5 root x, well, that's positive 35 root x. Okay, done with the inner terms. Last term, 7 times 2, and both positive. Well, that's 14. Great, so here is my result of FOILing. And now I notice that these are like radicals. Here I have the same index and same radicand, so I can combine them as like terms. And so my very final answer is 45x plus, well, 35 and 18 gives me 53 root x's plus 14. Great. Let's move on to problem number 31. And it says simplify as much as possible. Negative 7 root 18 plus 3 root 108 plus 3 root 48. And to simplify, we're going to use the product property of radicals, splitting each of these radicals into 2 separate radicals in each case. So let me set it up for success. I'm going to say this is equal to negative 7 times a square root with perfect squares times the leftovers square root. Okay, plus 3 times a perfect square root and then a leftover square root, and then plus another 3 times a perfect square root and a leftover square root. Let me show you how I break this down. See, the 18, it's a multiple of a perfect square. And in your list of perfect squares, you would find 9. And if you multiply 9 by 2, that gives you 18. So I put a perfect square and the leftovers here and here. Okay, let's move on to this next piece of 108, and I'm going to break it into its pieces. When I see 108, I think it's a multiple of a perfect square possibly. Okay, so 108, well, it's also a multiple of 9, right? So I could technically put 9 here. 9's a perfect square. And what's left over is a 12. But 12 breaks down even further into 4 times 3. So I could break this one into, well, let me say it this way. So I'll show you clearly. 12 I can turn into 4 times 3, right? Which 4 is also a perfect square. And so I could put this 4 in the good square roots stuff, right? And then the 3 is all that's left over in here, okay? So I'm putting all the perfect squares in the first square root and then the leftovers here. And now I move on to this last piece, 48. Well, I know that 48 is a multiple of a perfect square of 16. So I'll put 16 here and then 3 here. That's the leftovers. 16 times 3 gives me 48. Okay, now that I've done this, I can clean it all up and I can say this is negative 7 times, well, the square root of 9, which is 3, times the square root of 2, plus, well, 3 times the square root of 9, which is 3, times the square root of 4, which is 2, multiplied with the square root of 3, plus 3 times the square root of 16, which is 4, times the square root of 3. Okay. Now, negative 7 times 3 is negative 21. and that's multiplied with the square root of 2. Plus, well, 3 times 3 is 9, times 2 is 18, which is multiplied with the square root of 3, plus 3 times 4, which is 12, times the square root of 3. And lastly, I see that these are like radicals. This one's not a like radical because it doesn't have the same radicand of 3. It has a 2 in it. But these are like radicals because they have the same, they're both under a square root, so same index, same radicand. So we can combine them together as like radicals. And so my final answer is negative 21 root 2 plus 30 root 3. Yeah, because 18 plus 12 is 30. And there we go. We have simplified as far as our brains will allow us to. Okay, and by the way, we just wrote our answer using radical notation, right? We're using radicals in our answer, not decimal notation. Problem 32 says simplify the radical expression and assume that all variables represent positive quantities. So the square root of 10 over 36p to the fourth. Now, I'm going to separate the single radical into two radicals using the quotient property of radicals. Okay, so I'm going to write the square root of 10 on top, and that's divided by the square root of 36 times p to the fourth on the bottom. And what I like about what I see on the bottom here is 36 is a perfect square, and p to the fourth is a perfect square. And when you square root perfect squares, they come out really clean, right? So, 36, its square root is 6. And the square root of p to the fourth, well, that's p squared. And the top up here, the square root of 10 doesn't simplify any further. So I can't split it apart into, clean it up in any way. Okay, so I'll just leave it as the square root of 10 on the top. And this is my answer. Great. Let's work on rationalizing the denominator. We never want our final solutions to have radicals in the denominator of a fraction. So looking at this denominator, oh no, we have a radical and another radical. And one detail about this is that there are two terms in the denominator, right? Terms are separated by addition and subtraction. So here I see two terms. The square root of y is the first term. The square root of v is the second term. And so to rationalize the denominator, when you have two terms, we're going to multiply by the conjugate of the denominator on top and bottom. Okay, so little reminder about conjugates. When you have two terms, the conjugate is the opposite sign from what you see. Okay, so the conjugate of the square root of y minus the square root of v is the square root of y plus the square root of v. Okay, so conjugate is opposite sign between the same two terms. And we're going to multiply that same thing on top and bottom. Okay, so we take that denominator that we just wrote out, that is the conjugate of this, and we write it on top as well. Because anything divided by itself equals 1. This stuff divided by this stuff, it's 1. And multiplying by 1 is the same thing. But what this helps us do is rationalize the denominator so there's no more roots in the bottom. And what we have to do is we have to FOIL not only the bottom, but we also FOIL the top. We FOIL both the top and the bottom in this case. And so I start and I say, well, first terms multiplied together, negative 4 times root y. That's negative 4 root y. Okay, now outer terms. So negative 4 times root v, well, that's negative 4 root v. Okay, let's keep it going. Now we have the inner terms of FOILing, so I'm going to take y and multiply it with root y, and I get positive y root y. And now last terms, y times root v, so I just get positive y times root v. Okay, so just write it out. It doesn't simplify. You just take this times this, and then add it with this times this, and then this times this, and then this times this, right? Now let's FOIL the denominators and see what happens. Well, in this case, we get the square root of y times the square root of y, which is y. Okay, so first terms, Good. Outer terms, square root of y times the square root of v. And so you could turn this into a single radical with y and v inside. Right? We just use the product rule of radicals. The square root of y times the square root of v equals the square root of y times v. Now the inner terms. Well, I get a minus square root of y times v when I multiply the inner terms together. Negative because of this minus sign right here. And then the square root of v times the square root of y, I can write it like this. And then the last terms are multiplied together. The square root of v times the square root of v is, well, there was a negative, so negative root v times root v, that's negative v. There we go. Now, the great thing about foiling conjugates, right, is that the outer and inner terms of foiling always cancel. So this term and this term, they are the same value with opposite signs, so they cancel each other. And perhaps I'll write the final solution down below. So I'll say that this is equal to, well, my cleaned up denominator is y minus v. And looking at my numerators, it looks like none of my terms are like terms. Okay, so I can't really do that much. I'll just leave it the same. So I'm just going to leave this as negative 4 times the square root of y minus 4 times the square root of v plus y times the square root of y, and then plus y times the square root of v. Looks like, I have like radicals, like the square root of y and the square root of y and the square root of v and the square root of v, but I have variable coefficients and, numerical coefficients, so it won't clean up too easy. I'm just going to leave it like that. Awesome. So that was our answer. I'm sticking to it. And we're going to move on to problem number 34, which is the final problem of this review. And it says to rationalize the denominator of the expression, the square root of x over 3y, and write the expression in the form of a over b with no square root symbols in b. Okay, assume x and y have the same sign. So what it wants me to do in the end is to rationalize the denominator. Okay, that's the objective. So I'm going to take what I have, the square root of x over 3y, and I'll show you what I do. First, I want to use the quotient rule of radicals to separate the single radical into two radicals, like this. Next, I'm going to rationalize the denominator by multiplying by the denominator's radical divided by itself, like this. Okay, so I looked at the radical of the denominator and I multiplied it by itself on top and bottom of this fraction, because dividing anything by itself is the same thing as multiplying by 1, right? So this divided by this is 1. Like, students always ask, how is that? Well, if you take 2 divided by 2, the answer is 1. If you take 187 divided by 187, the answer is 1. If you take the square root of 3y divided by the square root of 3y, the answer is 1. Okay, so this right here is just 1. Multiplying by 1 keeps the thing the same. But what this does is it rationalizes the denominator. And so I'll show you the answer. The answer is going to be, well, on top, the square root of 3 times x times y. So I'm just multiplying these three things together. And I'll write it like this. The square root of 3 times x times y. And then on the bottom, the square root of anything times the square root of that same thing is equal to that thing without the square root anymore. So I have 3y. Right, let's explain that. If I have the square root of 2 times the square root of 2, the answer is 2. If I have the square root of a grumpy college student times the square root of a grumpy college student, the answer is grumpy college student. So if I have the square root of 3y times the square root of 3y, well, what's the answer? Yeah, you got it. The answer is 3y. Okay? Now, there is no more radical in my denominator. It's okay to have a radical in the numerator. What's not okay is to have a radical in the denominator. Mathematicians hate it. And so my answer for the numerator stuff, right? A is the numerator stuff. Well, that's the square root of 3xy. That's my answer. Okay. And then the denominator is 3y. No more radical, right? 3y is the answer for the denominator of that fraction. And there we go. We are all done with this chapter 2 and 8 review. Lots of questions, lots of things that are making you think at this point. And that's really good. You've learned a lot of new stuff in math for these chapters. Thank you so much. Have a wonderful day. I'll see you in the next one.